So now we're going to talk about higher order derivatives, which is the last topic in this section. And we'll start by talking about notation. So when I have a first derivative and my dependent variable is called y, we call the first derivative y prime. If it's in function notation, it's f prime of x. If we want to write that in Leibniz notation, we write it as dy dx, operator notation, d dx of f of x, and then the second, this is usually used more in like Calc 4 or Calc 3. Our second operator notation is capital dx. So this column is our operator notation, Leibniz notation, and then these are our prime notations. So if you just do a first derivative, it's pretty clear how that works. If it's a second derivative, we just say y double prime or f double prime. The Leibniz notation gets a little bit weird. So it's d squared y dx squared. And what you really want to think about that is like there's a parentheses around the dx. So we're doing like d dx of something. And if we just kind of pseudo exponent notation, the two d's would be the d squared, and then the dx, the whole quantity, would be squared. So it can be a little bit confusing for people, like why is the squared here on this one and there on that one? There probably really should be some parentheses there. So here's our second order operator notation, and then notice here we have the squared. We almost never use this one, so I wouldn't worry about this notation too much. If we have a third derivative, just triple prime, the exponent here becomes a 3 in our Leibniz and operator notations. Once we start getting 4 and higher, in the prime notation we put a parentheses, so this isn't an exponent. The parentheses is supposed to indicate that it's a derivative. And then of course a 4 here, and so on. So nth derivative, y, and then it looks like it's to a power n, but it's not really. So example 7, we are going to find a third derivative of this k, and this k function has a product, and then we'll check with Wolfram alpha. So we need to take the derivative 3 times. If I want to take the first derivative, I just go ahead and do the regular product rule. So in our product rule, remember we're adding, so much like the quotient rule, we have 2 parentheses, but we add instead of subtract. So I have first derivative of cosine is negative sine plus second, which is cosine derivative of p with respect to p is 1. So notice in our Leibniz notation, we're taking a derivative with respect to p. Let's go ahead and simplify. So minus p sine p plus cosine of p. And there's nothing I can do to factor or make that look any better, so we'll just go ahead and leave it like it is. Okay, and that was actually k prime. I just realized I wrote k, but that was my k prime. Okay, if I want to find k double prime, I just take the derivative of this. So if I want to find the second derivative, I just find the derivative of the derivative. Okay, and again, we're going to need a product rule on this part and just a regular derivative for the second part. So we'll go ahead and template out our product rule plus, and then we'll have a derivative of cosine there. So let's go ahead and take the derivative of cosine because that one should be an easy one. So negative sine of p. And now we're going to work on just this part, and that's what's going to go right here. So our first is negative p. The derivative of sine is cosine plus the second sine of p. Derivative of negative p is negative 1. Now we simplify. Negative p cosine of p minus sine of p minus another sine of p. So there actually are some like terms now. Negative p cosine of p subtract 2 sine p. All right, now we do it one more time because we wanted to find the third derivative, and I'm calling it k triple prime, but in the end, we can write that that was the third derivative of k with respect to p. Okay, product rule again on this guy. So, and then minus the derivative of 2 sine p. So again, we go with first, minus p, derivative of cosine, negative sine p, plus second, cosine p, derivative of first, negative 1, and then our very last term is our derivative of negative, or 2 sine p, because I've already got the negative there. So the derivative of 2 sine p is 2 cosine of p. And then we will simplify, so I get p sine p minus cosine p minus 2 cosine of p. And when we combine our like terms, p sine p minus 3 cosine of p. We'll say that that equals our third derivative of k with respect to p. Before we check in Wolfram Alpha, I want to go ahead and do a little bit of pattern recognition. So I'm going to look at the original function, the first, second, and third derivatives. So my notation up here is in our Leibniz notation. And so our original function, let's see, it was p cosine p. Okay, and then our first derivative was negative p sine p plus cosine p. Our second derivative was negative p cosine of p minus 2 sine p. And our third derivative was p sine p minus 3 cosine of p. And whenever you have sine and cosine and you're doing multiple derivatives, there's going to be a sort of pattern that ends up coming through. And in that part, that has to do with our relationship between sine and cosine derivatives. So we learned that in a previous class, that we follow around that way. And so when we're doing sine and cosine derivatives, we kind of always go through positive, positive, negative, negative, some sort of pattern like that. But since we were starting with a cosine, we went positive, negative, negative, positive. So if you look at what's happening here, our sign on the first term goes positive, negative, negative, positive. Now, if we think of this as really a 0 times a sine of p, and then we can kind of see that our signs go not positive, but positive. The sign is positive, so positive, positive, negative, negative. And the coefficients in front of this second term go 0, 1, 2, 3, if we just look at their absolute values. So I'm just going to make a stab at what I think the next derivative would be, and we'll check when we check in Wolfram Alpha. So I think it's definitely going to be p cosine of p, and we went positive, negative, negative, positive, so that should go negative because we've completed that. Nope, it's going to go positive again. Sorry, we need to have 2 positives. So it looks like there's always a p at the front, and then it goes sine, cosine, sine, cosine. And then here we have gone positive, positive, negative, negative. So we're going to go positive again, and we should go for sine of p. So let's check our third derivative, and then let's see if I was right on my guess from the pattern on the fourth derivative. Okay, so I'm just going to check my third derivative first. And unfortunately in Wolfram Alpha, even when you go to this math input area, they only go up to a second derivative. So if I want to get a third derivative, I need to kind of nest some commands. So I'm going to do ddp. What's going on here? Oh, get my keyboard up. Okay, so ddp of, and then I'm going to grab that command again. But instead of the first derivative command, I'm going to grab that second derivative command, which is right here. Okay, and I'm not sure if this works. I may have not given it enough parentheses, so we will see. And my original function was p times, and I'm not going to do implicit multiplication. I'm going to actually tell it I want to multiply cosine of p. All right, let's see what happens. Okay, so it looks like it did do a derivative of a second derivative, which would give us our third derivative. And right down here, we can see that that is giving us p sine p minus 3 cosine p. Now switch to this notation here, which means partial derivative. We don't need to worry about it switching to that notation. The partial derivative for what we're doing right now will be the same as the regular derivative. Okay, so I'm going to go back and I'm going to check my fourth derivative, and I accidentally deleted what I had inside there before, so I'm going to have to retype it, but I'm going to do a second derivative of a second derivative with respect to p, and then we'll put our function in there. So p times the cosine of p. And you could, of course, just use x here if you prefer. And it gives us, just in a slightly different order from what we had. So if we look at their answer, they have 4 sine of p plus p cosine p, which is the same exact thing that I guessed. Okay, the last example on this page is to find the second derivative of k equals secant of t. So we'll start by taking the first derivative, k prime, and to do this, we remember our trick. And we don't even need to write the other ones, because if we want to keep secant, then our derivative is secant t tangent of t. And if I want to do the second derivative, now I need to use a product rule. And I might have to write kind of small in this, because we're going to do first secant of t plus the derivative of tangent. And remember, if I want to keep tangent, then the answer is secant squared plus, and I'm going to go ahead and color code that like I've been doing. Now we keep the tangent and we multiply by the derivative of secant, which is secant t tangent of t. So we end up with secant cubed of t plus secant of t tangent squared t. Or if we take a secant of t out, secant squared t plus tangent squared t. Now, just out of curiosity, I want to see what happens if I check this in Wolfram Alpha. Okay, so I've already typed this into Wolfram Alpha, and I can see I did second derivative, and it gives me exactly the answer we had. I thought they might do something with either the tangent squares or the secant squared, because there is a Pythagorean identity related to those, but they just left it like it was. If you scroll down, oftentimes there will be some alternative answers, but none of the answers here look any better than what we started with. So when you're checking in the back of the book or you're checking against Wolfram Alpha, just know that the answers might look slightly different, but a good way to check if they're the same is just go ahead and graph them if you're not sure.